Okay, good morning, everybody. Hope you're having a nice Saturday morning.
Good morning.
Last time we started exploring some of the early history of electricity. And we saw where everything got started, and we saw that once again the ancient Greeks were at it because they had amber. And they first wrote about amber and about how it was very special and about how it had this power of attraction that they couldn't explain and they attributed to the gods. We saw how 2 millennia later, electricity became something a lot more ordinary. How people discovered it wasn't just amber that had that power, but even ordinary window glass did. Then we saw how 30 years after that, people figured out that electricity is not just something you could create, but also something that you could transport along a wire. Then people figured out that there is not just one electricity, but two. Today we call them positive and negative. Back then they were called vitreous and resonance, as we found. And we also saw how in a Leyden jar, both of those electricities come together to form a very efficient means of storing a large amount of electricity. And then finally, by the end of the 1800s, or the early 1800s, late 1700s, we also saw how this dispute between Galvani and Volta led to the emergence of a second kind of electricity, voltaic electricity, that came out of battery. Okay, it sort of looked similar, but it also looked very distinctly different. And we also met some of the people who were behind these discoveries. And one of our heroes last time was Stephen Gray, who in his retirement came up with that discovery of conductivity. He was the one to send electricity down wires. And that was very much a chance discovery, if you remember. He started out in his retirement room, playing with a glass tube and figuring out that even though he rubbed the tube to electrify it, the feather that he used as a detector, it was attracted to the end of the tube where he stumped it with a cork. That you could just have shrugged that off, but he didn't. He pursued, and he tried many different things. And so he tried all the possible things that you could try, and in the end he had a relatively good idea of what worked and what didn't work. And he figured out that it wasn't, the thinness of a silk thread that prevents electricity from going through, but it's actually a distinction between metals that conduct electricity and silk, which does not conduct electricity. Now we also saw that there's different kind of discoveries that require different kind of personalities to make them. And our hero there was Charles Dufay, who, due to his upbringing, was very disciplined and very rigorous, and he went through systematically to electrify all kinds of different materials. And he discovered that there are two kinds of electricity, that some materials, if you rub them, they get charged one way, or electrified one way, and other materials, if you rub them, they would get charged another way. There is no way that he could have made that discovery had he not gone through this entire list of material, and that requires perseverance and dedication, which, he had plenty. Now, if you look at all of those discoveries, you will notice that there were no precision instruments whatsoever. Electricity as a phenomenon was so apparent that people relied exclusively on their senses. Okay, remember Stephen Gray had this feather that was attracted to the glass tube, or he had paper snippets that were flying up a bowl. People felt electrical shocks from the Leyden jar and so forth. There was a very clear sensory experience that they used to notice electricity and to figure out some of its properties. And we also saw that there is one giant big elephant in the room still, which, came up at around the same time as the ancient Greeks wrote about amber, and that is lodestone, or magnetite. Magnetism, as the Greeks wrote, this stone too has the power of attraction. And it was clear to them that they are superficially similar, but they're also very distinct. So what is going on? And this is where we'll continue the story today, and we will actually resolve that long-standing mystery between electricity and magnetism. And our first hero here is somebody who grew up in Denmark, Hans Christian Ørsted, who grew up in a very scientifically minded family. His father was a pharmacist, and so that was the notion of science that he was endowed from a very young age. And he was a very gifted student. And he was somebody who was interested not just in science, but also in philosophy. But not philosophy in its own sake, but philosophy as a way of guiding his scientific thoughts. And in particular, he was enthused by the philosophy of Kant, sort of the idea that there is some underlying harmony in nature and that there must be some unifying explanation that talks to all of those various different phenomena that one observes in the natural world. After he finished his studies, he was awarded a travel scholarship. 3 years he could travel around the continent in Europe and immerse himself in the various different scientific schools that were in existence then. And he met like-minded people. In Germany, he ran into Johann Ritter, who was thinking about very similar lines about the unity of nature and such, and the two of them had a lot of fun together. In fact, he encouraged us to keep pursuing this line of approach. Now, I mentioned Ørsted was a great scientist. In fact, he was the first one to extract aluminum from aluminum ore and make it into its metal form, albeit in a very impure state. Back then, he called it argillium. Today, we call it aluminum. And Ørsted would continue to be philosophically minded, and towards the end of his life, he wrote a book, a collection of essays about the soul there is in nature, and that speaks to all of this variety of phenomena that one has. So that's the mindset that he had, and so it's not surprising that he would also wonder about the connection between electricity and magnetism. And that was around 1820, so 20 years after Volta's discovery of the battery, his invention of the battery. And so electricity was very commonplace and easy to come by in the lab. And he muses, so he writes in 1820, the reasons for and against an essential resemblance between magnetism and electricity might seem to be nearly balanced. Each of them consists of two powers, or directions of powers, of an opposite nature, submitted to the same laws of attraction and repulsion. So he says, if I take two magnets and I put them such that they point in the same direction, north-facing, they would repel. If I turn one of them around, so they point in opposite directions, suddenly they would attract. And he puts that side by side with what we heard about Dufay. If you put two positively charged or two vitreously charged bodies together, they would repel. If you put a glass tube and a piece of paper, they would attract. Almost as if what was happening in the magnets was that one part was positively charged, the other part was negatively charged. Suddenly, if you flip the orientation, the force changes. And so he tries to think about how one might follow up on this thought. If we imagine a voltaic pile, it would have the most perfect analogy with a magnet. Again, voltaic piles, his batteries, being the common source of electricity. So he says, if I have a magnet, one face is north, the other face is south. If I take a voltaic pile, one side is plus, the other side is minus. It must be tested whether electricity in its most latent state, so contained in a battery, has any action on the magnet as such. Okay, so he says if I put a magnetic needle next to a magnet, the needle will clearly react or will move. So would it not also be possible if I put a magnetic needle next to a battery that's charged, would it not also move, given this analogy that he had in mind? And he tried it, but there's nothing. But then he remembers something else. As we also saw last week, since Ben Franklin's days, people understood that lighting has something to do with electricity as well. I called attention to the variations of the magnetic needle during a thunderstorm. He noticed that the magnetic needle that he had in front of him would twitch every time there was a lightning bolt. So he says, let me try to recreate this. Can I make the magnetic needle react to some kind of lighting I can produce in the lab? I expected the greatest effect from a discharge associated with incandescence. Okay, lighting is very bright, there's light being emitted, it's very hot. So that's what he tries to recreate. And he does the following. He takes a magnetic needle and he runs a thin platinum wire along the needle. And then he connects that to the battery that he has. And the reason he uses a thin needle, a thin wire, is that such that once he makes contact, electricity would flow and that thin wire would start to glow. It would get very hot and it would start to emit light, just like the lighting bolt he has in mind. The magnetic needle, though included in a box, okay, he puts it in a box, was disturbed. But the effect was very, very feeble and no particular law could immediately be observed from it. The experiment made no strong impression on the audience. In fact, he tried this experiment during a lecture he was giving in the winter of 1819-1820. And you can very clearly imagine if I did this experiment here in front of you, I had my small little box with a magnetic needle, those sitting in the back would not even see what's happening. And so it's very clear that it did not make a strong impression on the audience. To him, it did make a strong impression, though, because he was very surprised. But as he mentioned, he could not immediately figure out what was behind this, how the needle reacted. So what is the magnetic effect of an electric current? There was clearly something going on, but what was it? Many days of experimenting were required before I could find the law governing the effect. As soon as I had discovered it, I rushed to publish the work. In fact, he puts aside, once he had made that observation in his lecture in the winter, he puts it aside because he's very busy with other things. And he only comes back to it about 8 months later in July 1820. And then he sits down and he puts in the time required to really study it and see what the law was. And he goes through different ideas that he tries out. The first of his ideas is that maybe the magnetic effect is in the same direction that the current goes through the wire, the electricity flows through the wire. Right? And that's also something that is sensible, because if you have a magnet that he uses to guide his thoughts, the magnetic action is greatest at the ends of the magnet, where the poles of the magnet are. And it's weakest on the sides. Right? So in a sense, the magnetic action is parallel to the direction of the magnet. And so maybe, he says, if there is electricity flowing through the wire, maybe the magnetic action is also the same direction as the flow of current through the wire. And so what he does to test that is the following. He puts the magnetic needle in the north-south direction, which it would naturally go, and he would put the wire in the east-west direction, his thin platinum wire connected to the battery, and then he would turn it on. And what he would expect, of course, is that if the magnetic action was the same direction as the current, the electricity, then the needle would turn, because it would sort of follow the magnetic action of the wire. But nothing of that sort happened. And in fact, he points out in his writings that he was not the first one to try, that many others had tried that in vain and also failed to produce an effect, so that it was maybe stupid to try it in the first place. Others would have already discovered what was going on if that was really the case. But then he goes further. He concludes that if the magnetic action is not in the direction of the current, maybe it's sort of lateral to the current. Maybe it's perpendicular to the current. And that's, again, something that's maybe not unheard of, because after all, if you have a bolt of lightning, the light that comes out, and that's why you see it, also goes laterally to the magnet, to the lightning bolt, right? It goes laterally to where the electricity is flowing. So maybe, he says, if my current goes upwards, maybe the magnetic action goes sideways in my wire. And he again puts it to the test. So now what he does is the following. He again takes a needle, north-south, and now he puts the wire parallel to the needle, okay? And he puts it either to the left of the needle, or he puts it right on top of the needle, or he puts it to the right of the needle. And then, let's think this through. If indeed the magnetic action was coming out laterally out of the wire, you would expect the following to happen. If the wire was on the left side of the needle, the magnetic action would sort of push it away from it, would push it towards the right, and the needle would rotate clockwise. If the wire was to the right of the needle, the magnetic action would push the needle leftwards, and it would turn counterclockwise. And if the wire was right on top of the needle, nothing would happen whatsoever, because the needle would sort of simultaneously be pushed left and right, and it would not feel anything. But that's also not what happened. What happened was the following, that every single time, irrespective of where he puts the wire relative to the needle turns left. The needle turns left even in that center situation where the wire is right on top of the needle. Okay, imagine how mind-blowing that is. If I put my pointer here and I balance it on my finger, and I manage to do it exactly right, so it stays in balance, it stays in balance because the left side looks exactly like the right side. And the pointer cannot make up its mind which way to tilt. Same situation here. If the wire is exactly on top of the needle, how can the needle make up its mind whether to turn left or right? Both sides look the same to the needle. And yet, every time he tries it, the needle turns left. Okay, something very profound is going on. So what is the law that he claims to have found in the end? And the law, as he puts it, is unexpected and inexplicable. And the law is the following. The law is that there is a force that goes around in circles around the wire. It goes laterally to the wire, but it doesn't come out straight. It goes around the wire in circles. So let's see why that works. Here's again the three situations that he tried. If the wire is on the left side of the needle and we have this circulating force, if you will, the force comes in and pushes the wire towards the left. It pulls it in. On the right, the force comes out and sort of pushes the needle away. It also turns left. And in that case, even if I put the wire right on top of the needle, and the wire is above the needle, then the force would still push the needle towards the left. Okay, so the rotation goes in that sense. If I put my thumb upwards, because that's the way the electricity is flowing, then the way that my fingers are pointing, my remaining four fingers are pointing, would be the direction of that magnetic force. Okay, that would explain, he says, why the needle always turns left. Okay, if there is such a circulating force that goes around the wire, this is what would happen. In fact, this is what he did observe. But as he said, it's both unanticipated and inexplicable. Nobody had ever even conceived seriously of the idea of there being a rotating force in nature like that. But it was real nonetheless. This was true bona fide magnetism from electricity. Electricity, magnetic action on the needle, but it was a very strange kind of magnetism, and people didn't understand why it looked like it does. Now, the landscape of electricity in 1800s, when we left off last time, was the following. We had the ordinary electricity, or common electricity, glass globes rubbed by cloth, being charged up electrically. We had voltaic electricity, because of Volta's invention of the battery. And then, that was also the age where animal electricity became widely known, electric eels putting out electric shocks to defend themselves. Now, in 1820, after Ørsted's discovery, there was also electromagnetism. There was magnetic action generated by electricity. And it was nonetheless confusing. Now, last time I promised you that it will get worse before it gets better, and this is the first time such something like this happens. It will get still worse today before it gets better. And in fact, the person who made it both become worse and then suddenly make it become better is the same person, and that's Michael Faraday, who was an apprentice to a bookbinder in London. Here is the bookshop that he was working in Rebow's, but he didn't really find the bookbinding business to be intellectually stimulating. In fact, he dreaded his work there, and he was rather bored. Now, in London at these days, there was a wonderful place called the Royal Institution. And that was a place for education, where science was being taught to the general public. Lecturers would come in, scientists would come in, and give public lectures. And if you're wondering who founded this wonderful place, it is none other than our old friend from Munich, the uniform inventing, tree planting, soup inventing, jack of all trades, cannonballing Count Rumford. Through his pass through London, before he came to Munich, he founded the Royal Institution, and this is where Faraday went to take his minds off the bookbinding business, and he came there and he listened to lectures by Humphrey Davy, who was a chemist. And he greatly enjoyed the lectures. Davy was a wonderful lecturer, and here you can see him lecturing in front of a large crowd. People were interested in hearing what he has to say. In fact, Faraday, after his lectures, presented him with a bound copy of the notes that he took of his lectures, with probably the idea of maybe getting a job from Davy to finally be able to leave his bookbinding business, but Davy, in fact, encouraged him to continue binding books. Until Davy's lab assistant was fired because he was staging a fight in the Royal Institution, and suddenly Davy was in need of a lab assistant, and he remembered Faraday. And so then Faraday became Davy's lab assistant, and this is how, in 1820, he moved with his wife into his new quarters in the Royal Institution, because the post as a lab assistant came with lodging included. So he and his wife moved into their room at the Royal Institution in 1820, and this was also when he received a letter by his friend Phillips, who was the editor of a philosophical journal. And Phillips writes, "Dear Faraday, I write you this just to jog your memory that we expect from you this month, and as early as suits you, the remainder of the history of electromagnetism." So Faraday had been contracted to write up a history of electromagnetism for his journal, and it was clearly sort of running late, and so Phillips sends him the reminder. Now, this was 1 year after Ørsted made his discovery, and so Faraday thinks, I better go back and reproduce Ørsted's experiment and try to immerse myself into that field so I can actually write a good summary. So this is how Faraday gets in touch with Ørsted's work. Ørsted's discovery of that inexplicable rotating force around the wire. And this is where Faraday takes over. And he says, if I put this wire upwards, okay, Ørsted put it on the table, flat, but Faraday thinks if I put it upwards and then look at it from the top, what I would see is that force revolving around in that circle. I wouldn't see it with my naked eye, but I could make it visible if I take a compass needle. And if I then move that compass needle around the wire, the needle would also turn, because the needle would be following and continuing to point in the direction in which that magnetic force is pointing. Okay, so as I move the compass around, the needle would also turn. Now, Faraday had a somewhat unique way of thinking about magnetic needles, or a compass, that becomes very important because he thinks, or he imagines there to be, the poles of the magnet. So we just talked about the poles as somehow the end points of the magnet, where the magnetic action is the strongest. But Faraday thinks of them slightly differently. He thinks of them as there being fictitious points towards the ends of the magnet, where the force is really residing. Okay? So he says there is a blue pole and there is a red pole, both of which would somehow feel that external magnetic force, and the red one would sort of feel a pull in one way, and the blue one would feel the pull in the other way. However, there being always two poles in the magnetic needle, the needle itself would not move because they would just be pulling in opposite directions. The only thing it could do is turn. And so he says, I can imagine, though, there being a situation with only one pole. Okay, if I had half of a magnet that could move, then it would be evident, he says, that the pole of a magnet would also have the tendency of actually revolving around that circle of magnetic force. Okay? Or, necessarily, he says, I can also have it the other way around. The wire, in principle, could revolve around the pole if it was fixed. Okay? The idea being that if the force on that blue pole always points in the direction of that circle, then naturally, if that pole was sort of free to move on its own, it would continue to move around in the circle. And so this is what he wants to demonstrate, and he builds this wonderful apparatus, which is, in 1821, very soon after he took up his new job, the first electric motor. And it looks like it does because he uses it to make 2 points at the same time, 2 experiments at the same time. He would show on the left side that a pole in a magnet could indeed revolve around the wire, and on the right side he will use it to show the opposite, that a wire can revolve around the pole. So how does it work? There's 2 vessels that are filled with mercury on either side. Mercury is a metal, so it conducts electricity, but mercury is also a liquid, and so things can move through mercury effortlessly. On each side, he puts a magnet, vertical, but on the left side, the magnet is held in place at the bottom by a short thread, so it can move around freely, but it's anchored, if you will, to the bottom. On the right side, the magnet is fully fixed, and it's sort of set at the bottom of that vessel. Now he connects the left side to a battery, and the current would flow. It would come in, would flow through the mercury, up the wire that he puts in into the mercury, and then return back to the battery throughout the base of the apparatus. And of course, since Ørsted discovered that now there would be these rotating lines of force around the wire, that single pole that could move, the other one being fixed and held in place at the bottom, that single pole would now indeed revolve around that wire, as he had anticipated. The right side worked in much the same way. Current comes in, goes through the mercury and back down the base, but now it's the magnet that's fixed, and it's now the wire that sort of can trace around the circle going through that mercury. So he managed to show that electricity can not only produce magnetism, but electricity can produce motion. And that was the first of his big discoveries, and you have many electric motors in existence today. Faraday wasn't content simply using straight wires, he also investigated other geometries. So imagine, he says, if you twist the wire into a little loop, around the wire you would still have that weird revolving force that Ørsted discovered, but you could make them visible. If you put that little loop of wire on a piece of paper and you put iron filings on that paper, the appearance of these lines of magnetic force was extremely beautiful and instructive, he writes. The iron filings arranged themselves in lines, passing through the ring parallel to its axis and then folding up on either side as radii round to the edge. So exactly in these circles that Ørsted found. So that they represented exactly the lines which a pole would have described. Again, he thinks back to his view of magnets as there being 2 poles, each of which in principle would follow these lines if it was free to move. So at this point, it was clearly established that electricity can give rise to magnetism. Now Faraday, naturally, thinking about this very hard, was also wondering about the inverse. If you start from magnetism, can you go back to electricity? The hope of obtaining electricity from ordinary magnetism has stimulated me at various times. He was thinking about that since a while, and he wants to investigate that experimentally. the inductive effect, as he called it, of electric currents. I lately arrived at positive results. Okay, so writes Michael Faraday in 1831, okay, around 10 years after his first demonstration of that electric motor. And the intuition that he has is the following. If I have a wire through which I send some electricity, if I then put another wire very close to it, maybe some of that electricity could leak, if you will, into the other wire. Right? If I have a single wire, I can produce some magnetic action, as we already saw. But then maybe some of that magnetic action could be converted back into electricity and therefore show up in the other wire. Okay, that's his hunch that he has. And with that in mind, he sets forth to build an experiment. So what he does is try to put two wires together. Okay, and the way he does it is the following. He winds 26 feet of copper wire around a cylinder of wood, like a helix. And then he needs a place for the second wire, but the second mustn't touch the first, because otherwise it would just be conduction and not induction of electricity. So he covers that helix with a cotton cloth, which acts as an insulator, and then he puts the second one on top. Second wire applied in the same manner, which then produced, as he called them, two principal helices closely interposed, having the same direction and not touching anywhere. Okay, that's what he wants to make his experiment work. And then what he does, he connects one side, so one helix to his battery, to his voltaic pile, and he connects the other helix to his galvanometer. Okay, that's a device to measure electric currents, or flow of electricity, and it's a masterpiece of instrument design, so it's worth having a look. Because it works in a way that we can already understand and appreciate just from what Ørsted discovered. So here's how it goes. There is a needle on a scale that can turn because it's suspended on a very, very fine silk thread. So it turns almost without resistance, and it can show the flow of electricity. Now, there is two pins where you can really hook up the electricity you want to measure, and these two pins connect to wires that lead to a coil. Okay, he called it a multiplicator because many coils wound around, if you will, amplify the effect of that small current. And inside that coil would be a second needle. He called it the sensing needle. And if you send some electricity through it, that needle inside the coil, just like Ørsted's magnetic needle, would be affected by that current, and it would start to turn, and in so also turn the needle at the top, which you could read off. Now the question is, why is there two needles? Why couldn't I simply have done with one? Because in fact both of those were magnetic needles, compass needles, but they were oriented in opposite directions. Okay, so north points the same way as south points on the other needle. Now why is that necessary? Well, imagine if you only had one needle, it would also be a compass. It wouldn't measure just the current, but it would also immediately have a tendency to point north. But here you want to measure current, and you don't want to know where north is. But so if you put a second needle that's turned the other way, so it would point north the other direction, if you will, but it would exactly cancel out the pull that the other needle would feel. Okay, so an arrangement of compass needles like that would not actually function as a compass. It would function as an anti-compass, if you will. It doesn't react to the Earth's magnetic field at all. But that's exactly what he needs, because he wants to measure the current. He doesn't want his needle to be moving around just by the apparatus standing there on his lab desk. So that's why he needs two needles. And that's what enables him to make really, really fine and precise measurements. So that's what he does. And he looks at the needle in this experiment. And then he connects the circuit. When the contact was made, there was a sudden and very slight effect at the galvanometer. Okay, the needle moves a bit to the side. But whilst the voltaic current was continuing to pass through the one helix, the red one, no galvanometrical appearances of any effect could be perceived. The needle moves back in its original orientation, although the active power of the battery was proved to be great. Okay, he says, there's clearly a lot of electricity flowing through my red helix because the thing is getting hot. Okay, it's even starting to glow if you continue, but the needle is pointing back at zero where it was before I even contacted the battery. But then he says, there was also a similar slight effect, but in the opposite direction, needle moves counterclockwise, when the contact with the battery was suddenly broken. Okay, something was happening, but it was only happening when you turn the battery on and when you turn it back off. Whilst the battery is connected and everything gets hot, so there's really electricity passing, the needle doesn't move. And the way he phrases it is thinking about light and jars. It continued for an instant only, that effect on the needle, and partook more of the nature of the shock of a common Leyden jar than that from a voltaic battery. Okay, here is something, he knows the battery as something that provides a steady flow of electricity, but here, when he turns it on and when he turns it off, he gets something that's more akin to a Leyden jar that can shock people and produce an instant discharge. I could obtain no evidence by the tongue, by spark, or by heating fine wire of the electricity passing through the wire under induction. Okay, so there's clearly electricity in the blue side of the helix because his instrument shows it, but his instrument is exquisitely precise, and he has no other means of detecting the presence of that electricity. Okay, he touches the wires, which is how you sometimes see if a battery is still charged, because you will feel a prickling sensation. He didn't feel anything. He did many of the other tests that he knows to test for the presence of electricity, but none of them gave him a positive result. Only his very precise instrument did. And without that instrument, he wouldn't have made that discovery. And now we need to go on a little detour and then come back to Faraday. And that detour leads us to William Sturgeon, who was a shoemaker, but he was also in the army. And he was posted to Newfoundland as a gunner, where he was known to fix the shoes of his superiors in the army in exchange for them allowing him to read at nighttime. And this is how he would teach himself maths and physics and languages and also mechanical skills. At some point he would leave the army and he would return back to England, where he ends up at the town of Woolwich, which has a military academy. Okay, he's out of the military, but that academy still has lectures, and they're clearly interested in electromagnetism, and he makes contact with the people teaching there, and he comments on the state of the science of electromagnetism at that time. He says, "The science of electromagnetism, although so generally interesting, appears to be very little understood, in a great measure owing to the difficulty of making the experiments and the great expense attending the process." Okay, he says it's really interesting, but it's just very hard to do, and it's very expensive to do. You need batteries and these expensive but precise galvanometers and so on and so forth. It's not for everybody, it's for a few select people. Another obstacle is that the experiments being hitherto exhibited on so small a scale are by no means calculated to illustrate the subject in public lectures. If you think back to what Ørsted lamented, that the people at the back of his lecture hall didn't even see what his compass was doing, here's the same point again. Electricity was such a fine science that you really had to see it for yourself, otherwise you would not believe it. And the experiments that were done were so small that nobody could even see in a public lecture what was going on. So it was not well illustrating the point and the excitement that people felt about the science. And he says, he goes further, even when the experimenter succeeds to his wishes, which is not frequently the case, the experiment can only be seen by a very near observer, those in the front row. Others are obliged to take for granted what they hear reported. That's not very satisfying. And so he goes and tries to find a way out. He tries to amplify, if you will, or make stronger the magnetic effect by an electric current. Because that's what he says is needed to really demonstrate that science and have a big impact on a large crowd of people. And so he builds the first electromagnet. And that was just as Faraday was busy building his motors in 1826. So before Faraday started thinking about induction and such. And what he found is the following. He takes wire, and he also winds it in a helix, but not around wood, such as Faraday had done, but around metal. Okay? He needs insulating wire, which also hadn't been invented before then, because there was no need to insulate wire if you could simply wind it around wood. He found the following. If you wind wire around metal, upon making the galvanic connection with the battery, he closes the switch, the iron wire becomes a strong horseshoe magnet and will support a heavy bar of iron, the one here at the bottom, but on lifting the connection wire, the weight immediately drops. Okay? So he says, if I turn on the magnet, I close my battery switch, there is a strong force of there's a strong line of magnetic force that passes through the helix, much in the same way as we saw Faraday's iron filings pass through his single loop of wire, but here it would be much stronger because in some way that iron would channel those magnetic lines of force, and so the magnet would be strong enough here at the bottom to lift a heavy piece of iron. Now other people pushed that notion even further. In this country, Joseph Henry in Albany, New York, built even stronger electromagnets. You can again see that same horseshoe shape. There's a thick metal wire underneath, and he puts up 9 different coils. Okay, all made from insulated wire and all separate from each other, so he can hook them up separately or in parallel or together or none at all, to try different things. And he also built this wonderful contraption of his where he has this battery, and there is this horseshoe magnet with all of the wires coming out from all of those independent coils that he winds up. And then the rest of the apparatus is just to put a lot of load on that electromagnet. You can see there is that bar of iron that's held in place by the magnetic force, and there is a place down here where you can put additional weights, and there is even a long lever arm where you can put additional weights all the way at the end to really put a lot of mechanical force on that magnet. And he does many experiments with that to see what works well and what doesn't work. And in his 13th experiment, where he turns on all of his 9 coils at the same time, he manages to lift 650 pounds, okay, all from one battery. And so that's clearly something that's very illustrating and that's very impressive. And you can even show in front of a large crowd of people. And so this, if you will, achieved Sturgeon's goal of making electromagnetism more of a fun science and something that you could use to impress people. And so also Faraday heard about these magnet demonstrations of Henry's. And he also tries to see if he can use them for his purpose. By now he had been thinking about and playing with his early induction devices. And so he jumps on the bandwagon. He tries the following. A welded ring was made of soft, round bar iron, the same kind that Henry and company used in their magnets. Several helices were put round the ring. Okay, just like in Henry's magnet, you have different coils on that same ring. But now Faraday, has a closed ring of iron, whereas Henry's was that horseshoe type. But nonetheless, there's 2 coils. The helix B on the right was connected by copper wires to his galvanometer in the same way as we saw before. And the helix on the other side, on side A, was connected to the battery, as we saw before. And then when he turns on the battery, the galvanometer was immediately affected, and to a degree far, far beyond what has been demonstrated before. So he finds the same thing that Henry saw. If you put these lines of magnetic force through iron, the effect would be much, much stronger, because the iron, as it turns out, would actually channel and guide these lines of magnetic force. So also Faraday succeeds in making his experiments work on a larger scale and make them more impressive and astounding. And by now, Faraday clearly has a hunch that something is happening and that something has to do with change or motion, because it only shows up when he turns the thing on or when he turns it off, not while it's working. Okay? And so he tries to see if that battery is needed at all, because motion can also be produced, or change can also be produced in other ways. So he tries the following. A helix was constructed upon a hollow cylinder of pasteboard and connected with the galvanometer. Okay, there's now 1 coil, and there's no second coil, and there's no battery, but it connects the galvanometer in the same way. One end of a cylindrical magnet was then introduced into the axis of the helix, and then the galvanometer needle being stationary, he waits until everything is stable down, the magnet was suddenly thrust in, okay, with great force and great vigor, and immediately the needle was deflected. But then, with the magnet being left in, the needle, just as we saw before, goes back to its original position. And then the magnet being withdrawn from the coil, the needle was deflected in the opposite direction. So again, he finds the same thing that he had noticed before, that if you put something one way, the needle deflects. If you pull it back out, or if you turn off the circuit from before, the needle will move back the other way. But in this case, there is no battery, there is no second coil. Here, there is electricity from motion, and there is no electricity from magnetism as before. And he proceeds not just to point out that this exists, but he also tries to find a way of describing if and when this effect arises. He proceeds to find or to formulate what he calls the law of induction. And he prefaces his statement by saying, the law which governs the evolution of electricity by a magneto-electric induction, which is what's happening there, electricity and magnetism being turned into each other, that law is very simple, although it's rather difficult to express. Okay, and I'm giving it to you here in a slightly abridged form, and he says the following. If the wires, the ones in the coil, moves so as to cut the magnetic curves, then a current of electricity is evolved in the wire. Okay, that's a bit of a strange law, because what he is saying is these magnetic curves that he is talking about are the lines of a magnetic force, which he has already pointed out many times with his iron filing pictures. So he says whenever such a line of magnetic force is moved so that it cuts through a piece of wire, then and only then is there some electricity in that wire. Okay? This gives me the ability to make predictions. It maybe isn't a very satisfactory explanation. It might have been for Faraday, it wasn't for other people, but at least it gives them a way of making predictions. I can now tell whether this law is correct or not by trying it out in various different situations. And the nice thing about it is that it also works in that second example, Faraday's first, in fact, where there's no motion but there's only electricity. Now you're asking, if there is no motion, how can these magnetic lines of force cut through wires? Well, if you will, if you turn on that magnet, and at some point there will be these magnetic lines of force appearing that weren't there before, but whilst they are building up, they somehow must have moved through the wire so that they can appear on the outside. And so while they're moving through the wire, they're effectively cutting through the wire, and in Faraday's law, this is what is needed to produce an electric effect on the other side. But when everything is stationary and there is electricity flowing, these magnetic lines of force don't move anymore and there is no electricity induced. Only if then he turns the battery off and the lines of force collapse back down, they would cut through the wire in the opposite direction, and then you have the opposite electrical effect on the blue wire. So electricity in 1830s is the following. Not only is there now electromagnetism, there is now also magnetoelectricity. Goes back the other way. And in the 1830s, Faraday finally says, enough is enough. The progress of the electrical researches brought me to a point at which it was essential that no doubt should remain of the identity or distinction of electricities excited by different means. So he says, Faraday, now we have 5 different kinds of electricity. Are there really 5 different beasts, or are they all really just the same thing? And he makes a list. The various phenomena exhibited by electricity may, for the purpose of comparison, be summarized. So he takes stock of all of the evidence that is out there, and he makes a table. And he thinks about what are all the effects that people have found associated with electricity. Well, if you think back to Dufay, we know attraction or repulsion along sensible distances is something that electricity can do. Electricity can produce heat. It can make wires glow, as we also saw. There are physiological phenomena. If you think back to Galvani's frogs, muscles can twitch. Biological organisms are affected by electricity. Electricity can produce sparks, as we saw in the early demonstrations of Leyden jars. And of course, there is magnetism, which we now also know is something electricity can do. So all of those different phenomena are properties and manifestations of electricity in different ways. And Faraday's object now is to compare the electricities from different sources to see if all of them can really produce the same effects. Okay, so he says, if all of my 5 different electricities can produce all of those different phenomena, then they are really just the same kind of electricity, because if it looks like a duck and it swims like a duck and so forth, then it probably is a duck. So here is Faraday's table. Different rows for the different kinds of electricity. We'll take common, friction, magnetoelectricity and animal electricity, and along the columns, the different effects. Physiological effects, magnetic deflection, so on and so forth, and he proceeds to tick all of the boxes one by one. For example, he shows that voltaic electricity can produce sparks. If you take a battery and you short it out, you will get a spark. And in fact, he says that brilliant star of light produced by the discharge of a battery is known to all as the most beautiful light that can be produced by art. Okay, he was really poetic about his sparks that he could produce. And so he goes through his entire table, and he also ticks all the boxes for common electricity that can be stored in a Leyden jar. And for example, here he says that if he takes a Leyden jar and he discharges it through a wire that he runs by a magnet, the magnet reacts in exactly the same way as if I had taken a voltaic battery and I connected it to the same wire. And the positive side of the voltaic battery is just like the positive side of the Leyden jar. There is really no essential difference. And so his general conclusion that must be drawn from all of this collection of facts is that electricity, whatever may be its source, is identical in its nature. So there is only one kind of electricity, and that kind of electricity now starts to conquer the world. And the first big application of electricity was in communication. Because by now, people know how to build electromagnets. They know that electricity can travel down wires. And if you put the two together, you get a telegraph. The first telegraphs were needle telegraphs. Okay? You can imagine there's a bunch of compass needles arranged on a board. Here's a real picture. There's 5 needles on a board. And then on the board would be engraved all of the different letters. And then all of those needles, there would be an electromagnet sitting behind them with long wires attached to the other side of the telegraph. And then whoever was operating the switches on the other side could make each needle move, either to the left or to the right, and thus signal to the person looking at the board which letter they wanted to send. Because if these two needles were turned on, that would point to the letter G, because that's the only one where the two needles would intersect. So that was the first telegraph that was put in commercial operation in the United Kingdom, going out of London along a stretch of the Great Western Railway that runs all the way up the west coast of the UK. But it was not very practical. And one of the reasons it was not very practical is that if you have 5 needles, you need 5 wires if you want to turn all of the needles on separately. So you need to run a string of 5 wires all along your telegraph, and that's very expensive. And you need to invent mechanisms to prevent the wires from touching, even in winds and so forth. It's very complicated. As a result, this scheme didn't really find widespread adoption. Another scheme, therefore, that doesn't have these detriments found widespread adoption, and that was the single-wire telegraph by Sam Morse. Now, he found that you don't really need 5 needles to signal all of the letters. You could do it with 1 wire, and you would have a telegraph key that you could use to send rhythmic patterns of short and long signals down a single wire, and then the person on the other side would be tasked with converting these signals back into the letter that you wanted to send. Okay, so there's some code involved, which today we know as Morse code. Now, Morse also had to battle a second problem, which is how to really make that signal travel along very, very far distances, many hundreds of miles, because if you just run it down a wire, at some point the signal would get too feeble to be able to be detected on the other side. So he needed repeaters, or as he called them, relay stations. So along his telegraph line, he would take, every 20 miles, he would put a station with a battery and an electromagnet. After 20 miles, the signal was still strong enough to actuate that electromagnet. That electromagnet would then be powered by that local battery and would effectively retransmit. There would be a telegraph key at this station operated by the electromagnet, remote operated by the station at the back, and so forth, so that the signal would effectively start from scratch again, could travel another 20 miles until it reached the next repeating station, another 20 miles, and so forth, which meant that at the very end of the chain, you could have another one of those electromagnets in the end actuating a printer or producing audible tones you could listen to in headphones. And so then you can travel arbitrary long distances if you just have these repeaters in Morse's scheme. That was in 1847, and in 1857 or 58, another big step was made. The first telegraph cable was laid to cross the Atlantic. It went from the most western tip of Ireland across the Atlantic and then hit land again in Newfoundland, and then there were additional cables that brought it back down to the US. 1858, first message sent through that first transatlantic cable. Here's the message. Directors of Atlantic Telegraph Company, Great Britain, 2 directors in America. Europe and America are united by telegraph. Glory to God in the highest, on earth peace, goodwill towards men. A very noble message. That cable didn't work very well. It broke down after 3 weeks. Many cables were put in place since then, and of course, as we will see at some point, next time probably, the telegraph was soon made obsolete, and another scheme replaced it. So that was the state of the art of electromagnetism in the 1850s. Now things start to fall into place. We have one kind of electricity, as Faraday said. This one kind of electricity can produce magnetic lines of force that show up beautifully in Faraday's iron filing pictures. We know that we can turn electricity into magnetism. If we send it through wires, we get these weird circulating lines of force. And Faraday also showed that we can turn magnetism back into electricity if we have the right situations. If you have a magnetic field that cuts through the wire, if you have these magnetic lines of force cutting through wires, you can turn magnetism back into electricity. So this starts to really be a big branch of science at that point, where things finally start making some sense. But the question is really, Faraday was able to discover these things, and he was able to describe if and when these phenomena appear. But the question remains, how does it actually really work? Are you satisfied with this idea of there being lines of force that cut through wires and then magically the electricity appears in the other end? It's not a fully satisfactory explanation. And there was one person who also didn't find it to be a fully satisfactory explanation, and that person was James Clerk Maxwell. He is also an Englishman from Scotland, in fact, in the UK, and he is one of the few truly great physicists. And just to illustrate a bit what kind of caliber of scientist we're dealing with here, he wrote his first scientific paper at the age of 14, where he showed how with pen and paper and with some rubber bands, you can make a contraption to draw ovals in different ways on a piece of paper. You can draw ellipses, you can draw pointy ones and such. He generalized, if you will, what an ellipse means in geometry. Later on, he also looked at Saturn. People knew Saturn since a very long time. They had observed it through telescopes, and they had observed that it has these rings. But people were puzzled at how the rings could stay in place instead of breaking up. Maxwell turned it around and said, well, since we observed that the rings stay in place and don't break up, we must conclude that they are not made from solid material, because that it would indeed shatter and not withstand the force, but indeed be made of small ice crystals or small particles that all move independently and that just to us, because we're far away, appear as a solid ring, a solid body. He was also the first to demonstrate in a public lecture at that Royal Institution in London the first durable color photograph. And if we had had more time in the early days of this lecture series, where we talked about heat and the kinetic theory of heat and about how molecules move in a gas and how that means that the gas has a certain temperature, Maxwell also put that on solid foundations. And he figured out exactly which fraction of molecules moves at which speeds and how that turns out to be related to temperature. Okay, so Maxwell did everything, if you will. And so, it shouldn't be surprising that he was also really intrigued by magnetism. And he asked, what really happens around the magnet? I can see all of those pretty pictures of these iron filings, but what is happening? And he goes back to Faraday, because he really appreciates Faraday's notion of magnetic lines of force. And he says, the beautiful illustration of the presence of magnetic force afforded by this experiment, the iron filings, naturally makes us think of the lines of force as something real. Right? He says, this is not simply a nice illustration of there being some magnetic effects around the magnet, but maybe there's more to it. We are dissatisfied with the explanation founded on the hypothesis of attractive and repellent forces directed towards the magnetic poles. Remember, Faraday was content with having poles attract and repel and follow along the lines of force. Maxwell accepts that as a way of describing what happens, but he doesn't accept it as an explanation. We cannot help thinking that in every place where we find these lines of force, some physical state or action must exist in sufficient energy to produce the actual phenomena. Okay, so he says clearly somehow the iron filings arrange themselves in these beautiful lines, so something must be present at the point of the iron filings to make it happen. Otherwise, how would the iron filings know to orient themselves? And you can clearly see Maxwell is again troubled by this idea of action at a distance. Two magnets attract or repel depending on how you orient them, but what happens? He doesn't buy into this idea of action at a distance. And so instead, he tries to again look at it from the other direction. He starts with Faraday's lines of magnetic force, and he tries to come up with an explanation, or a description, if you will, of the phenomena that people had observed, starting, not ending, with magnetic lines of force. So he says, we come to consider the magnetic influence as existing in the form of some kind of pressure or tension in the medium. Okay, so he says if there are really some force lines that Faraday pointed out, and I accept them as something real, then these force lines must be existing in some kind of medium, some magnetic medium that fills the space. If we observe the lines of force between two magnets, okay, that are oriented like this, so they would repel, we observe that, when the lines from the poles avoid each other and are dispersed into space, the poles repel each other. So he says, if I put two magnets like this, I would feel a repellent force. But if I look at one of Faraday's iron filing pictures and I look in the space in between the magnets, I would actually see the lines of magnetic force be less dense. It appears as if the lines were also repelling each other, and as a result, as a consequence, the magnets would be repelling. Okay, so he puts the lines, the magnetic lines, front and center. He says he appears that if the stress in a line of magnetic force is like a tension, it's like that of a rope. Okay, so he really thinks of these magnetic lines as something real, like little metal wires that are bouncy and stiff, and they are the ones that feel each other's presence, and as a result, the magnets push apart. I propose to examine magnetic phenomena from a mechanical point of view to determine what tensions in a medium are needed to produce these kind of mechanical phenomena that we observe. So what properties would these magnetic lines, which he presumes to be real, have to have for the magnets to repel in the exact way that people measured, okay, quantitatively? And he says that if he is successful in doing that, not only would he have found a totally separate way of explaining Faraday's phenomena and such, but it would also be, if you will, a bottom-up view of all of those phenomena, and would be a way to greatly enlarge the knowledge of this part of physics. So here is the idea that he comes up with. And he, again, draws inspiration from Faraday. He says, we know that when electricity circulates in one of Faraday's loops, it produces lines of magnetic force passing through the circuit. Right? We saw that. If electricity rotates in the wire like this, you have these circular forces around the wire. And now Maxwell tries to see what happens. He tries to fill in the blank of what happens inside that loop of wire to make all of those magnetic lines appear and go through the loop of wire. And he says, well, clearly there's some electricity moving around in that wire, and so that electricity would maybe excite some kind of vortices around that wire, and then the entire space inside the loop of wire would also be filled with vortices that would rotate in the same sense as the current would flow in the outer loop. And through this mechanism, the effect that I generated at the place where the wire is would be transmitted to the inside of that loop of wire. But then he says, if you look carefully and all of those things rotate in the way that I do, then they would clash in the middle, and I need to insert small little wheels that sort of balance things out, like cogwheels. I need to insert spacers so that they don't touch and they don't sort of, crash into each other. And then he says, at every place where I have one of my little vortices, this is where a magnetic line of force starts, or where it passes through. Okay, so in all of those places, with all of those little vortices, there is a line of magnetic force that's associated with it, and it points sort of through that little vortex. Okay, so these pinkish wheels are the ones, like for cogwheels, that you need to insert if you want the two big ones, these original vortices, to be all turning in the same direction, which is what he proposes them to do. And so these are Maxwell's rules. You can have vortices that rotate counterclockwise. You can have vortices that rotate clockwise. You have all of those pink spacers wheels in between to make them from crashing. And then you would have a place where you have vortices that go counterclockwise and counter vortices that go clockwise. So there is some boundary separating them. And this is what an electric current is, okay, in Faraday's rules. The electric current is something that separates clockwise and counterclockwise in the vortices. Now, you might find these rules a bit ridiculous and fantastical, and I would agree with you. And in fact, Maxwell also found great difficulty in conceiving of the existence of all of these wheels and vortices in a medium that are all side by side, revolving in the same direction about the same axes. Okay, so Maxwell was clear that he is using that idea not because he likes it, but because it works. And in fact, these rules, although we today phrase them and explain them in different terms and using different words, are still the same rules that we use today and that people studying physics will learn. Maxwell's rules turned out to really describe how electricity gives rise to magnetism and how magnetism can be turned back into electricity. In fact, Maxwell's explanation was one of a very peculiar kind, because it turns out, under the right circumstances, not only can electric currents generate vortices, but the vortices themselves, if you do it right, can generate more vortices. And then these vortices can generate additional ones and so on and so forth, so that if you have a wire and you set it up right, you would have these vortices that sort of move away from the side of the wire in all directions at a certain velocity. Under the right conditions, there is some disturbance in that magnetic medium that you can generate, and that disturbance can propagate far away from the place where you put the original current from your original battery. And Maxwell, doing his pen and paper calculations, he put everything down quantitatively. He could calculate what the velocity would be that this disturbance moved away from the wire. And he calculates it to be a ridiculously high speed, 193,000 miles per second. And then he pauses, and he says, recently, a gentleman from France, Monsieur Fizeau, has measured the speed of light in air through a very beautiful, complicated experiment, and he finds light to move at 195,000 miles per second. Okay, so here Maxwell is truly flabbergasted. Here's one thing. He started out thinking about magnetism and electricity on a piece of paper, not looking out into the real world, sitting there in his study, and he finds that not only are there these disturbances that I have to accept as a consequence of my vortices and such, but I can even calculate what the speed of these disturbances is, and it turns out to be almost exactly the speed of light. So then Maxwell. The velocity of undulations in our hypothetical medium agrees so exactly with the velocity of light that we can scarcely avoid the inference that light consists in the undulations of the same medium, which is the cause of electric and magnetic phenomena. Okay, if you will, he took a big and bold step, he post-dicted the existence of light. So he goes all the way, he says, look, these people thinking about optics and telescopes and such have measured that light travels at that speed. I, coming from the other direction, from electricity and magnetism, have found that there is something that hypothetically could move at the speed of light. So maybe what these people have known as light rays is actually what I was thinking about all along. And so Maxwell's vortex model is really amazing. He started out trying to find an explanation for electricity and magnetism. He did find that, but he found a lot more. He found that with these vortices, he could describe light and how rainbows form. He could describe how mirrors work and how telescopes work. And from that perspective, his model stands apart from all of the other ones that we had found. If you think back to Hauksbee's electrical spider webs that he put in his glass sphere, if you think back to Dufay's two kinds of electric, the resonance and the vitreous one, or even if you consider Franklin's electrical atmosphere as an electrical medium that he expected there to be, all of those models are explanations that can explain the facts they were constructed to explain. Some even failed at that. But Maxwell's was the only one that implied additional consequences that the model was not intended to explain. In fact, Maxwell had no idea whatsoever that he would find the existence of light related to the existence of electricity, and yet that conclusion was forced upon him if he took his role seriously. Now, of course, there would be great consequences, technological kind, coming out of Maxwell's vortex theory. My voice is transmitted to the speakers using his undulations in that hypothetical magnetic medium, but that's a story for next time. Thanks a lot. I should also point out something important. Next week, November the 4th, we're actually going to be in a different room, not this one, but room 120. It's also written on the board. So it's most convenient if you enter by the north entrance, then you can have a level entrance to that lecture hall. It's just next door, just to make sure you find your way. Thanks. Questions?
Maxwell had a mathematical education.
Yes.
Did he actually formalize this field theory?
Yes, he did. So Maxwell...
He wrote it down as sort of a hydrodynamic whole.
That's right. So very good. So Maxwell actually did not simply formulate all of this verbally or in writing, he actually did it with mathematics. So fluid dynamics. Say again?
It's like Stokes.
Oh yeah, exactly. That's right. Exactly. So Maxwell obviously was living in his times, okay, late 1800s, where mechanics was very big. Okay, mechanics of all kinds of bodies, mechanics of solid bodies, mechanics of liquids. So it was natural for Maxwell to think of these vortices, as, if you will, vortices in your bathroom sink, as something that exists in some medium that could be a fluid. Maxwell gave it the name of a hypothetical magnetic medium, but he could use all of this mathematical machinery that other people had developed for the study of how liquids move and how vortices can exist in liquids.
He came up with the wave equation.
He wrote down all of this, not in the way that we teach in schools or universities today. He did have the wave equation. He had exactly the same equations that today we associate with Maxwell's name, written in a different form. So later it was Oliver Heaviside who actually streamlined, if you will, the way that Maxwell's equations are written. Maxwell, in many ways, used mathematical notions that were outdated, that we're not using anymore today, because he was fond of them and he was sort of practiced in using them. Other people found them opaque and not very easy to grasp. So there were other people who had an intention to reformulate, not change the nature of what Maxwell wrote, but simply describe it in a different way. And that is how, eventually, the modern Maxwell's equations emerged that we teach today. Yes. And today, maybe I should also say that. I mean, Maxwell was very keen on saying that this is an analogy with some real physical system that he has in mind. He uses that liquid, this hypothetical liquid of this magnetic medium, as something simply to have a concrete idea in his mind as he was fleshing out the mass. And although today we still teach the same rules, we have simply sort of gotten rid of that notion of there being some medium. Okay, so that thing that was useful for Maxwell to guide his thoughts in writing down the mathematics was useful for that, but it turned out not to be useful for much else. And in fact, people found it to be cleaner and nicer if you simply didn't have to talk about this hypothetical liquid, but you just use the vortices. Okay, then you have to ask, okay, vortices of what and so on, but in physics we have learned that some questions have very difficult answers and they're better not asked, so to speak, because the answers are not really illuminating. That's right, they got rid of the medium. That's right.
So I have something to ask about this Faraday electromagnetic induction and the galvanometer needle moving when you turn the switch on and off.
Right.
And not when the current is running at full strength.
Right.
So when this was explained in a previous lecture series a long time ago, I raised a question with the lecturer which had some continuing discussion that we never really fully resolved. But so my conceptualization is that, or my understanding of it is that you have a current that goes from a zero value before you make the connection, and then it goes up to a maximum level, and it takes some time to do that.
Right.
And that change from zero to the maximum is the time when the needle moves.
Right.
And in reverse, when it goes from the maximum value to zero, that's the other time when it moves. And so, again, I don't have a lot of confidence in my ability to articulate this question, but as I contemplated this, it seemed to me that we relate the action to change. And human beings recognize change by making comparisons between one set of observations and another, and either we write them down and record them, so that's a form of memory, or we just remember what we saw a moment ago and how it differs from what is now. If we add in some ideas that came later, such as the atomic nature of matter, with electrons circling a nucleus, you have a postulate of an ability of an electron to sense change and to react to that. And it has no memory by which to compare what came earlier
Right.
and what came later.
Very good.
Which led me to call it an anthropomorphism in the sense of ascribing to the inanimate object a power which only human beings seem to have by force of memory.
Yes.
So it seems to me like an objection to the idea that there's something fundamentally conceptually difficult about
Yes.
this.
Very good. So maybe to paraphrase the question, Faraday phrased the law that he found, the law of induction, as relying somehow on that concept of magnetic lines intersecting the wires, right? And sort of the process of intersection is some sort of change, and that's what produces sort of that electricity that's induced, and that's what you pointed out. And it's true. Faraday's law, in the way that he describes it, is a description of what he saw. It's not an explanation, or he doesn't intend it to be an explanation for what actually happened. Because if it were an explanation, you could exactly have that objection. Right? So if this is supposed to explain, why things work, well, then it better also explain how that electron sort of can have a notion of change, right? And then you would get into big trouble. And in fact, that speaks to a very general point about science, in my view, which is what is the difference, if there is a difference, between a description and an explanation? If you describe something and then somebody else finds a different description that is, if you will, leaner and more robust and requires you to jump through fewer mental hoops in getting there, but both, give the same answers, then that latter explanation, if you will, would be a better explanation because it required you to accept fewer things to arrive at that conclusion. And science, in my mind, this is getting very philosophical, science, in my mind, is only about finding descriptions, but finding better and better and better descriptions. So Faraday's description was clearly a description that he wrote down as a human being, having in his mind that idea for a very long time of his magnetic lines of force and so forth. So it would be natural for him to use that mental picture to describe what's going on. Other people later on, Maxwell being one of them, found different descriptions for what's going on, right? In totally different terms. In Maxwell's theory, there is no line of magnetic force. That would not be, if you will, an axiom, that would be a consequence of all of those vortices. The vortices are all there are, and then everything else emerges as a result. And the vortices move and they twist and turn in the way that they do, that his rules stipulate. And as a consequence of that description of vortices, Faraday's findings would follow. Okay? So in Maxwell's theory, that, if you will, picture of there being lines intersecting wires and such would show up, but in a very different way. He wouldn't have to explicitly mention that. It would come out as a consequence of his other postulates. So in that sense, Maxwell's description is a better description than Faraday's, because it doesn't require you to use this anthropomorphized notion of lines intersecting wires and such, which are all macroscopic things that are ultimately made out of atoms, and the atoms have no idea of them being part of a wire, right? And so as time progressed and the science went on and on and on, people have found better and better and leaner descriptions of what's going on. And today we also have a description of what's going on, and it has 19 free numbers, and it leads to all of that. The question is it an explanation or is it still a description? Okay, at this point you start being philosophical. I would say it's still a description. We don't know if we will ever have a true explanation of what's going on. But the final, the essential and central conundrum is exactly that. With any description, you can always ask, but why is this the case? Right? And then you will immediately run into trouble. Why is the world this way? Why is it not in another way? Why does this work as opposed to something else? Right? You can give an answer to why this is the case, but only in terms of another description. And then you can play the same game again, and so on and so forth. And very quickly, you will bump into the fundamental bounds of our knowledge.
So when I had this previous discussion with the prior lecturer, I only was addressing Faraday's electromagnetic induction, but he generalized the question to Maxwell's entire theory. And I'm not sure I understood this because I don't know Maxwell's theory that well, but basically he said all of Maxwell's theories, the different formula, the equations, all contain the same form. And so there's a question of change in each of those equations.
Yes.
And so I'm not clear that Maxwell, his description is better, at least in this narrow sense of this, containing the idea of an inanimate object responding to a recognition of change.
Very good. So again, it depends on how you decide to think about Maxwell. So it's true that there is one way of thinking about his vortices that really pictures them as being real entities, and they move and they change and such. And again, you would have that notion of change. What Maxwell's theory also has is a totally different way of thinking about it that in some ways still has change, but in a lot of a weaker sense. It sort of averages over all the possible ways that these vortices could have moved but didn't. Okay, in some way, the thing that really happens that to us seems to have some change and some sensitivity to change is only what you perceive, because what you see is somehow the average of all the possible things that could have happened and all the possible ways in which it could have changed. Okay, there's still change involved at some level, but it's a lot sort of weaker, because now you admit there to be many other possible evolutions of change. And the thing that we see is only sort of the average of all of them. So, you can play this game arbitrarily, and it's an excellent point. I'm not sure science at this point has a good answer. It has ever more abstract answers that always talk to some facets of your objection and your point. But there's always still another facet that lingers around. And in my mind, that's really a consequence of the fact that science at the end is done by humans. And we find certain concepts to be very intuitive to us. And that's why we use them in describing what's happening in the world around us. And gradually, as science got more and more mature, people abstracted more and more, and they invented new concepts to talk about these things, but at the end, it's still a human-centric game, because we're humans. And maybe at some point we will have a way of really talking about this without any biases or blindfolds that we're inevitably wearing, unless somebody else comes around and points out another objection. So it's an infinite game. Yes?
I have a question about the failure of the transatlantic cable.
Right.
Engineering, or was it some electronic reason why?
It was both. Okay, let's see. So this is a very funny story. So the way that this happened is that there's always multiple parties that are interested, and this was also a joint venture between different people. And the first big challenge I had to solve is how to actually have that cable come across the Atlantic without breaking. Right? So they had two ships, each outfitted with a big reel of cable that was sufficient to cover half the distance, and the two ships, they sailed to the center of the Atlantic, and then they sort of sailed back to back. One went to England, the other one went to Newfoundland. Now, before they could even get to that point, they had to produce that cable. And no single cable manufacturer was prepared to produce that much cable on such a short notice, so they had to split it between two different manufacturers. So now those two different manufacturers, each producing sort of their share of the cable, they twisted the strands of the cable in opposite directions so that the cable couldn't be spliced together directly or it would unwind itself. So after they had produced all of that cable, they discovered that they couldn't simply connect it, but they had to have some impromptu apparatus that would hold the cables together, made the electrical connection, but did not allow the cables to unwind each other. Okay, at this point, they could load it on ships and sail out to the Atlantic, and sail back to back, at which point the cable would inevitably rip, several times. And then they had to outfit another ship with a giant hook to pick up the cable from the mid-Atlantic ridge, to fix it. And they had to do that a couple of times until eventually the cable was there. It was lying on the ground of the Atlantic, and there was an electrical connection between the two continents. At this point, all of the engineering mess was resolved. Now the electrical mess starts. Because I spoke about Morse having these repeater stations every 20 miles or so. This cable didn't have repeater stations. Okay, there was simply no way to put them in the middle of the Atlantic. There's no way to put batteries in the middle of the Atlantic to supply them and so forth. So you had to find a different solution. And now there's two ways forward. You can either drive a very high voltage through that cable, a huge amount of energy into that cable, such that at the other end, you could attach, if you will, a standard Morse receiver that would give you a signal in your headphones that would actuate a printer that printed the message on a piece of paper tape. Or you could run it at a much lower voltage, a lot more casually, if you will, but then you need an exquisitely precise galvanometer to pick up the signal. Right? It wouldn't simply be sufficient to listen into your headphones, because that low voltage signal traveling across the Atlantic would be too weak to do that. In fact, people had invented an even more precise galvanometer than what Faraday had. It's called the mirror galvanometer. And it was sufficient to actually pick up those very weak signals if you sort of drive the cable at a much more lenient pace. Now, there were these two camps, and they wanted to do the opposite things. Some people wanted to drive at high voltage and get normal signals they could listen to. The other camp wanted to, don't push the cable too hard, but then they needed this mirror galvanometer to really hear out the signal. And so the inevitable happened. At the beginning, they drove high voltage signals through the cable. This was the time when there was a lot of media attention and people wanted the message. So, after all, after that initial message there was Queen Victoria was supposed to send a message to President Buchanan in the United States, like, state-level official things. And so it was important to get it right, and that's why they went with the strong signals. But the insulation of the cable wasn't good enough to really withstand that high voltage. And the insulation was damaged as a result of them starting out with that extreme high voltage, drive pulse. And so they couldn't get the message through with that original scheme. And they tried and tried and tried, and it took, around 17 hours to read out that entire message through that transatlantic cable, because they had to restart and then restart again and so forth as the insulation was giving way. Until they finally were prepared to go the other way and use that mirror galvanometer to finally get their message through, to rush it through for sake of their publicity. But then once that initial event was over, they wanted to go back and simply, push the cable harder and harder and harder with their high voltage drivetrain until the insulation was totally ruined and the cable was useless. And that happened after 3 weeks. And then, you went from all of this, effort to lying a cable to it then being electrically useless 3 weeks later. Because people were just pushing too hard. And obviously, people learned a lot from that adventure. There was a second and a third and so on transatlantic cable, where people had better technology, they were prepared, they knew what to expect, and so forth. Right? So it was really a pathfinder, if you will.
Engineering mess and a lot of money spent.
Absolutely. Yes.
How did they keep the Mid-Atlantic Ridge Banker from cutting the cable in half?
So it did cut the cable.
Oh, it did?
Yeah. So not immediately, but so the cable was very thick and robust. There was, the strands of metal wiring in the center. And then I think it was roughly that diameter, and most of that cable was actually rubber, to insulate it and give it a lot of mechanical strength. So it wasn't easy to cut it, because you can imagine it also had to withstand a lot of, tension. I can pull on that cable really hard, and it mustn't break. So they built it, very rugged. But of course, it was still a mechanical thing that could rip, and it did several times. Sorry, yes?
Out of curiosity, from your standpoint of science, with description and explanation, where do you fit prediction from that standpoint?
Right, very good. So a description is also something that can apply to future situations, to hypothetical future situations. Right? Because science happens over time as a result of, as we saw, many historical accidents, and things could have gone a different way. But a description, in principle, is something that doesn't necessarily have to talk to something that already happened. But in principle, you can also describe what's supposed to happen in some hypothetical scenario that you haven't really tried yet. Right? And you can sort of follow through with your thoughts, and that's what, in my mind, is a prediction. Okay, a description of some hypothetical result in some hypothetical scenario. Yes?
Yeah, on this Maxwell coming up with the something close to the speed of light, the experimenters said 195,000 miles per second.
Right.
Came up with about 198,000 miles per second. So they were fairly close together, maybe about 1.5% or something like that.
Right.
But they're both off from the actual value. How does that happen, that the fudge factor was the same in Maxwell's theoretical calculations as in the people that were doing the experiment? What experiment were they doing? How were they getting this? Were they like doing shadows? Were they like doing the light with off and on and from a hilltop to another hilltop, 10
Right.
miles away or something?
So there were many experiments that people did to measure the speed of light in many different ways, independently. One of which was the one that you pointed out, where you take two stations, you put them at some distance so that you have direct line of sight. Two hilltops, would be fine. And then you have some mirrors that rotate on either side, and you sort of shine a beam of light. And then if the mirror is exactly rotated right, it will point the beam of light back, and you would receive it. But if that mirror was turning very quickly, you had to time it sort of exactly right to get the reflection. Otherwise, it would be sort of pointing away from you, and you wouldn't see the reflection. And so, by exactly figuring out how you had to time the mirror to get the reflection of the light back, you could measure, in effect, how long the light would take to travel there, then reach the mirror when it was exactly right, and then travel back to you. Okay, that was one way of measuring it. Another way of measuring it would be on a tabletop, not requiring sort of faraway hilltops to work, using the fact which people didn't know at this time, that light in many ways reacted as waves, as Faraday pointed out. Opticians, people who built telescopes, they knew about interference. So they could build an interferometer on a tabletop where they sort of saw a pattern of light, dark, light, dark, light, dark, that then also enabled them to extract from that observation what the speed of light would have to be for that pattern to be the true one that you observe. Now, all of those methods, so Maxwell here cites one of them, sort of as evidence for his proposition, obviously have their own imperfections, and so none of these numbers should be regarded as really precise. Unfortunately, Maxwell doesn't write what the uncertainty is on that number, and if people did, say again.
There's no plus or minus.
Right, exactly. So there should be, the value of an experiment is never, in physics anyways, is never a number, it's always an interval. Right? So you do your observations and you do as best as you can, and then in the end you come out with saying, okay, I've done my due diligence, the answer is supposed to be, somewhere here. Okay, it's larger than this and it's smaller than that. But it's never an exact number, as Maxwell sort of wrote it in his paper. So, any experiment that's well conducted should really be an interval. It should contain uncertainty bands, which in this case would be totally separate. And there should be, if everything is really proper, such that if Maxwell's conclusion was true, should be such that they overlap. And then that would permit him to say, well, there is some true value that could be the same, but it's compatible with both experiments. Right? And that's sort of the standard of rigor that we have in experimental physics today. Now, obviously, this was more than 100 years ago when people were still figuring out and getting to grips with doing high-precision measurement. That's also something you had to learn, right?
Well, they got that close with such a primitive method.
Oh, absolutely. Absolutely. These people are not stupid.
Maxwell's off in the same direction, and he's off even though he was doing a theoretical calculation.
There's a 50% chance of that happening. So it's not unheard of.
Yeah, right. But what fudge factor was Maxwell using? It's interesting in a historical, I've never heard of this, that there's this coincidence that the experimental and the theoretical were off in the same direction.
Right.
By approximately the same amount. I'd like to look into it at some point if I ever have time. I've never heard about that.
Sounds good.
It was always like, oh, Maxwell discovered he had the speed of light from these equations, and how miraculous, blah, blah. And it's not that miraculous because, although they're close together, he's fudged his to
Yes.
be closer to the experiment.
Yes.
I don't know. If he was convinced, and if he got it right, that up there would say 186,000 miles per second. It wouldn't say 190.
So I think it's true. Maxwell was, so if the only thing you had were these two numbers, I would agree with you, right? I mean, maybe you have to have some mental gymnastics to really convince yourself that they're the same. But remember what Maxwell had going for him was that, his number had nothing whatsoever to do with all of these experiments. Maxwell had nothing whatsoever to do with optics. He was talking about electricity. So he was getting a number and...
That's the amazing thing about it.
Exactly.
You wouldn't think.
There's two numbers that...
Anything to do with
Absolutely. And that's why, even if they didn't match perfectly, for him that was still striking evidence. Because there's no reason that these two numbers would have anything whatsoever to do with each other, but they were relatively close. Yes?
Could you talk more about the galvanometer? Was that an invention of Faraday, or is he using somebody else's contraption?
That's an excellent question. I don't have the answer to it. I tried to find it out. The galvanometer, this is my conclusion, is one of those things that nobody invented, but that somehow just appears, and then everybody's using it. So,
I mean, the name, I always assume Galvani, but
it wasn't Galvani. People use Galvani's name for many things. Like even in common language today, it shows up. If I'm galvanized, I'm like, energetic. So, right. So I don't know who put forth the first galvanometer. There was many people who thought about magnetic effects from currents. Ampere was one of them. That's why today we measure electric currents in units of ampere, to honor him. And he was also the one who very carefully measured the forces and how they varied with the distance from a wire that carries some current. So it's conceivable that he would have had some instrument to measure that, and in fact he did, in a much more primitive sense. But what's more likely to have happened from my perspective, and that might be incorrect, is simply that once Ørsted's discovery was there, that wires produce magnetism and that can affect a compass needle, it was a long sequence of small incremental improvements to end up with ever more precise instruments. But the basic principle according to which they worked is always the same. Right? So there isn't sort of something that is the galvanometer, because it comes in many different shades and colors and variations. And so I don't know who built Faraday's instrument, if he did it himself, if he got it from somewhere else. I didn't manage to figure that out. Yes.
Historical question. We've already heard the story that it was Ørsted who opened and closed the switch and noticed the swing, and not Faraday who did this. But who really, is that story about Ørsted just urban legend?
So Ørsted. So the question was, so Faraday was the one who made the observation, the way I told it, that if you open and close a switch, you would get this effect on your galvanometer.
Was not Ørsted.
Sorry, what was the question?
It was not Ørsted then who did that.
So Ørsted did something. Ørsted, as far as I understand it, figured out that when you have a steady flow of current, you have a steady magnetic effect.
Okay.
What Faraday found out is that you still have a steady magnetic effect while that current is flowing, as you keep the switch closed. But there is a separate effect that Ørsted didn't know about, which is as you turn it on or off, as the magnetic effect is sort of ramping up and ramping down, while it's ramping, you would get an electric effect, okay, which is totally separate. Yes.
And so it wasn't Ørsted, it was Faraday.
Yes.
Okay.
Yes.
And just going back to Ørsted, that moment when he sort of lifted the compass out of that plane of the experiment, I mean, you sort of love to have been there. It seems, it seems both terribly obvious and terribly unintuitive. I mean, if you're just sitting there at the workbench, you're just moving things around, and you would think you would sort of stumble. Somebody would have stumbled upon. I guess he did stumble.
Yes.
But and so, I mean, in that sense, it's serendipitous. But
Yes.
It both changes everything, and yet it's something you would just so obviously come across. If you're
Absolutely. In hindsight, it's always obvious, and it's never clear why it wasn't discovered way before, right? But in the moment, like it's a coincidence, as you said, it's serendipitous. But even coincidences need to happen at some point, right? And that doesn't make them any less coincidental. I agree. Okay.
I don't know if I should not hold the class back and ask you after class. There's a question.
How long of a question is it?
It's about the magnetic field. Now, you can calculate magnetic lines of flux density, right? Magnetic lines of force. Is magnetic field continuous? Or if on a super duper duper microscopic level, calculating lines of force, there is no such thing as infinite lines of force per square.
Okay, very, very good. So,
Is there a place in space where there's no magnetic influence?
the answer is it depends. So that's slightly of a long answer. Maybe we should discuss it afterwards, if you agree. The two of us. If you agree, maybe we should discuss that afterwards. So people who don't want. I mean, people are free to stay, but you can also. Okay, maybe let's do it like that.
Okay.
Okay. Everybody's free to leave. Obviously, if people have more questions, you can stay around and we can chat.
Thank you.
Thanks.